special title. All right, please, Tudor.
Thank you. Let me share slides. And okay, is that working?
Yeah, yes, it works. Yeah.
Okay, right. So I did want to start by mentioning a few things that I completely skipped over last time that might bring some useful intuition into what happens this time. Um, and are kind of interesting features. So just to recall, so on Monday, my goal was to understand line operators and 3D topological field theories, which form a braided tensor category with various features. And I did it by using a pair of boundary conditions, and even having boundary conditions is a special thing. And when you do have them, that are transverse and complete, then one can create two dual Hopf algebras, and they're double, and the category gets represented by the double.
Tudor,
And
sorry, you see, it's still too many mathematicians in the audience. Yeah. So we should think about boundary conditions as some categories, maybe triangulated categories, or
no, so there. If you're really doing this in extended TQFT, they're objects in a two category. And I'll give
okay,
I'll
okay.
go slowly through some intuition on the next slide. What you can do is take their trace. If you have an object in this two category, you can take its trace and produce an object in the braided tensor category C itself.
And
And
the
this is
trace of an object in the two category is what?
so I mean the Hochschild homology. Um,
Hochschild
uh,
homology of this
so
object. Yeah, like for example, if naively we think about category, two category of all categories, whatever this means, you take a category, you take its Hochschild homology. Yeah?
yes, but that produces you a map, and in particular, it sends you can insert objects in there, and
So, and your whatever monoidal category, it's what sort of a bimodule categories for these, or how we should think about them.
sorry. So what I was going to say um, is also. I guess the pictures don't do much for you. This Hochschild homology functor for me is taking the boundary, the two-dimensional boundary, and wrapping it on a circle. And so what you end up with is something that looks like a thick line with that's empty on the inside and has the theory on the outside. Um, that produces not just an object, but a commutative algebra object inside. In fact, it's a commutative bialgebra inside the braided tensor category, and a lot of the questions, like a lot of the properties that I'm talking about, like having a boundary condition and then transversality and completeness and so on, can be accessed through these commutative algebra objects. Um,
So say
and
again, what's a commutative algebra? I missed.
it's the it's or sorry, I guess the word I really want is categorified Chern character. It's part of the Hochschild homology map. So I'm trying to take the Chern character of an object in a two category to get something simpler. to get an object in a one category in this braided tensor category.
Yeah, but tensor
And
structure comes from what? From endomorphism?
from the fact that it's on that Hochschild homology has to do with circles, and there are pair pants cobordisms relating circles.
I do not understand this intuition. I understand that probably you have some whatever surface with boundaries and you put Hochschild homology of whatever category on the boundary circles.
Yeah, absolutely.
Yeah, but this is familiar to mathematicians' story. It's something like they can construct TQFT, this kind of things.
Yeah. So it's the same picture that you're familiar with in two dimensions, where on a circle boundary, like you have a one category there, right? You have a like some A infinity category of boundary conditions, and um, you you can take objects in that category and label circular boundaries by objects in that category, and that factors through a Chern character map. You're no longer using the full power of the category, but you've taken Chern characters of everything, and
And this is a
you land in
two-categorical.
Hochschild homology,
Uh,
and that has a product from a sphere with three holes.
okay, all right.
And
So
this
this
is the
is
same,
okay.
except it's categorified.
Yeah, and your boundary conditions DNN, you have only two of them. Uh, I mean, two type of boundary conditions, like two colors. You know, this what you call.
Exactly.
It's sort of a
Exactly. Yeah.
operatic construction, and you color boundaries by letters DNN. Yeah, and then in the end you produce this somehow this semi-direct product is something which I should think associated with what? With kind of a cobordism or what? This U, whatever. How
Um, that
because you
is
yeah
it's roughly if there's enough dualizability around. Um,
assume that there is
I
enough
so
geometrically
yeah
this
yeah yeah. So I'm saying you can construct these. You can wrap these things in a circle, and you get two line operators, red and blue, that are algebras inside C. The fiber functor I've been using all along on bulk line operators is Hom out of the tensor product of these things. Um, and so what is U? It's the endomorphism algebra of the tensor product of these two lines.
okay.
That is one way to think about it.
Okay, maybe you'll continue because I have different model in my head, which actually has a perfect mathematical sense. It's a construction of quantum groups by Goncharov and Shen by using amalgamation procedure. And when you consider indeed connections on a disk with
Yes.
singularities, whatever, and but then it has precise meaning and
I
nothing
think yeah
mysterious.
and I don't think this is mysterious either, but there's I think that is that and the sort of Schrader-Shapiro construction of quantum groups that is related. It
I
is
don't know that construction, sorry. I better know Goncharov's work because he's my friend, so maybe because, but Shapiro also maybe has a construction. similar
But
to that.
but
All
but
right, but
I think anyway, I think that's a version of this picture.
yeah.
Um,
Mm.
if you try to compute what's going on in a particular case.
All right, all right. Please continue. That's
Um, s- in in a TQFT setting, the underlying spaces of the algebras around are spaces of states on rectangles. Um, and the quantum group appears on an annulus, and this is a thing that you see in these cluster algebra type constructions. Um, um, and given right anyway, that's a setup for actual boundaries, and there's a generalization for when you don't actually have boundaries, like in Chern-Simons. Um, and then the two Hopf algebras are algebra objects in some other simpler, ideally braided tensor category that I'm calling C-free. Um, so I was hoping to add some intuition by not really giving formulas, but just saying what you should think about in terms of Rosansky-Witten theory. So
you're too optimistic, assuming that people in the audience know what means Rosansky-Witten theory. They know probably mathematical interpretation of that story, but it's not really a theory. It's some, there were papers uh, uh, by Kontsevich, Kapranov, and whatever long ago in the 90s. But it's not about the
there's been a
theory.
great deal of work since the 90s that
Uh,
defines like the actual two category in
uh,
this
who, who,
example.
who defined the actual two category?
In limited cases, um, Kapustin, Rosansky, and Salina did.
It's physics.
And
It's not really, it's not, I believe that they
I
defined, but it's not really. Mathematically, last time I saw it, it was Roberts and Willerton or something like that. Again,
well,
it's more or less 25 or so years ago.
they define bratings, yes. Um,
But I don't know what should I have. So should I think that it's a two category, some two category, uh,
um, I
or maybe
sorry, like I don't I this it's not just physics work, right? There's an entire community doing derived algebraic geometry that is formalizing what it means to have a sigma model to a two-shifted symplectic stack in three dimensions, and doing geometric quantization in that context.
but
Um, like it,
yeah.
I just feel like I need to rebut the statement that this work stopped in the 90s mathematically. That's
No,
just
no,
not
no.
true.
Mathematically, probably
Um,
it continues, but the question is, what is the current state of art mathematically? People, I know names and people doing derived algebraic geometry, but as for Rosansky-Witten, I remember recently we discussed with Gukov one of his conjectures, and we found out that there were no enough foundational work on Rosansky-Witten which we can use
it
in a rigorous way. So that's kind of
I agree with some of that. Depends what you're trying to compute. Um, there are definitions in Robertson Willerton that are incredibly difficult to work with.
yeah. And so
Um,
who simplified or proposed something? How should I think? There should be, you see, it's not mathematics in a sense that we should have some pictorial or whatever mathematical object which we can understand somehow. Two category, that's fine. Two category with maybe some object in it, okay, that's also fine, perfect. Like holomorphic Lagrangian in the complex symplectic manifold, it's fine, or hyperkähler Reichenrosansky-Witten, that's good. You can associate a category to a holomorphic Lagrangian if it's smooth, like something like D modules or something like that, or whatever. There are many possibilities. Yeah, and uh, yeah, you
No,
can
that's
put.
fine. I think I want to move on a bit. If it's not a
Yeah, yeah,
useful
go
example,
ahead,
that
go
then
ahead.
I won't discuss it. I maybe will advertise some work of a student of Pavel Safronov's who is actually that should be out this month. That's defining um, it's defining Rosansky-Witten theory as um, 3-to-1 extended TQFT that should be useful in answering some
Yeah,
of your
sure,
questions.
sure. Do you remember
Um,
name of the guy? I know Safronov,
yes,
of course, but what's the name?
the guy. I mean, he's a young grad student. He's also called Tudor, actually.
Okay,
Um,
good. And
so easy to remember.
Tudor is good, but probably his last name is not Dimofte, so we can.
Yeah, yeah, no. His last name is Kaba.
How?
Um,
How?
Kaba, Caba.
C-A. Okay, go ahead. Yeah, thank you.
Cool. Um, anyway, so for anyone who for whom this is useful intuition, um, and there is actually so once you break down whatever bits of physics and math exist to actual categorical statements, those can then be proven. So the boundary conditions in this case are holomorphic Lagrangians in a holomorphic symplectic target. Um, the fiber functors you get from them
But
can be
what's the
written down.
category? What's the category? You said it should be objects. Do you take holomorphic Lagrangians themselves? Because even in the Fukaya category, you consider local systems or whatever on Lagrangian. So these are just supports. Object of the category is something else.
Yeah. So the best definition I have for that is what Kapustin, Rosansky, and Salina wrote down. Right.
And what
That's
did they write down? Yeah.
right. Yes. So the objects are holomorphic fibrations over, or they're coherent fibrations over holomorphic Lagrangians.
Uh-huh.
Um,
Okay.
and morphisms are given by categories of matrix factorizations.
Okay.
Um, anyway, um, let me maybe move on to the BPS stuff. I won't um, maybe say one more thing, but yeah. So I mentioned Koszul duality in the title of the lectures. Um, if we do things in a way that a physicist would call perturbative, but mathematically that means that all categories in sight are generated from their tensor identities. Um, and even if it's not true, you can work with the subcategory that is generated from the tensor identity. Um, then the expectation is that there's a Koszul duality between the Hopf algebras I mentioned and algebras of local operators. Um, in in terms of TQFT pictures, um, local operators form commutative algebras. There are local operators on each boundary, and there are local operators in the bulk that I'm describing without an index, without a subscript. And just like the Hopf algebras were associated to rectangles, local operators are state spaces on disks with both boundary and or D. Or the ones in the bulk are state spaces on S2, which can be split into an N disk and a D disk. And so part of what Koszul duality means between two algebras is that there's a canonical element in the tensor product that deforms the tensor product to something trivial by adding it to, well, if it's a DG algebra, by adding it to the differential, and in general by deforming the A infinity structure.
So say it again, because for me, for Koszul duality, whatever, the tensor product is not necessary at all. But so you said something which I should somehow understand.
I guess it depends on where you start and where you finish.
Yeah, good.
Uh,
Yeah, the simplest example for graduate students, and it's a Koszul duality. It's duality between symmetric and Grassmann algebra. So yeah,
yes,
good.
but one of those is in homological degree 1, and there's a more Cartan element in the product of the two that deforms the product to the trivial vector space. Um, I think that's just rephrasing um, the maybe the usual construction that one of these algebras um, is endomorphisms in the category of modules of the other one, of the trivial module.
Yeah,
This what
probably.
I'm giving you is a resolution of the trivial module um, as a bimodule for the two.
Mhm.
Saying that the product of the two deforms to C gives you a way to resolve C as a bimodule, and then that bimodule can be used to produce all the categorical equivalences
But
in
this
Koszul
deformed
duality.
thing, can I think of it as as an object which is quasi-isomorphic to the resolution of the diagonal, which represent the trivial
I
object?
think so.
Yeah.
Yes.
Okay.
Um, for what it's worth, there's a TQFT picture for that that involves gluing a circle to a disk. Sorry, yes, gluing a rectangle to a disk, um, getting a bigone and using transversality to deform the bigone to something trivial. Um, and in this sort of setting, the completeness condition I had described before, which is used in the gluing, induces the actual more Cartan element that defines this resolution of the trivial module. Um, the other last thing I wanted to mention related to last time, and I again this is in cases this is technology that's useful. Local operators in a 3D topological theory have an E3 bracket, or in cohomology a Poisson bracket of degree -2. Is that a useful or familiar statement?
Uh, Local 3D TQFT, local operators. Yeah, probably.
I
Yeah.
mean, it's the analog of the Gerstenhaber bracket. in two
Yeah, in
dimensions.
3D, yeah.
Uh,
For Gersten-Haber, for the Hochschild complex, it will be E2 algebra, and now it's E3. And I believe long ago we constructed with Maxim nice geometric interpretation of this E3 structure, but it's never been published. Yeah. All right. Good. Yeah.
um, so um, so on the physics side, there's a nice interpretation of really of the brackets on cohomology classes. Not, I think pinning down the full E3 structure is difficult. But the bracket in cohomology comes from integrating descendants of local operators along a hop flank. Um, and I just wanted to point out that I had mentioned this quickly before, that that hop link actually appears in the definition of the hop pairing for these two boundary hop algebras. When the hop pairing corresponded to inserting arcs or sparks on the boundary of a ball, and those can be pushed into the interior of a ball where they get completed to an actual hop link. And that's not an accident. Um, in um, so the inverse of the hop pairing is the R matrix, and in this Koszul duality between bulk operators and U, the quantum group, one expects the E3 bracket to, or the inverse of that, to become the R matrix in U, and this is kind of an explicit way for that to happen. Saying it all sort of fits. It fits together, and then if you have some mathematical formalism you want to interpret this in, go ahead and do that. Okay. Sorry, that's all I wanted to add to last time. Um, so I'm going to switch gears a bit. I don't know if I will make you more or less happy. I want to talk about some similar structure that arises from 4D holomorphic topological theories, which are even less well defined mathematically than anything I've talked about. However, I think some of the conclusions that one takes away are interesting. Um, so, right. So these are theories that are defined on manifolds built from patches that look like C times R2. I'll use coordinates X and T on the topological R2 bit and Z on C. Globally, they should have some sort of two-dimensional transverse holomorphic foliation. But everything I'll do here is entirely local. And an example of such a theory that's been used quite a lot recently is 4D Chern-Simons, that I think might have. I mean, it sort of sits between the holomorphic Chern-Simons that describes um, the space-time theory of the B model, and actual 3D topological Chern-Simons. And like Calabi-Yau Chern-Simons, you take the Chern-Simons 3 form and wedge it with the holomorphic volume form. And here you do the same thing, but wedge it with a holomorphic volume form on this copy of C. Which you have to choose. One choice in just a Euclidean setup is DZ. So this was introduced and discussed by Costello, and then in relation to Yangians, and then much more by Costello-Yamazaki and Witten. Another example of physical theories like this are so-called holomorphic twists of 4D n equals 2. And this comes in multiple flavors. There are, for example, gauge theories defined by a group and a representation. There are theories of class S defined by a Riemann surface. And both of these flow in the infrared to Seiberg-Witten theories that are abelian with some BPS states. And the BPS states have independent mathematical constructions, which is where things tie in together in interesting ways. Line operators in such a holomorphic topological theory, no matter which flavor, due to the invariance in the holomorphic topological directions, are expected to form something that goes by many different names. It's something that Jan formalized decades ago. And I think you called it a meromorphic braided category. Sort of generalizing meromorphic tensor categories that have an OPE but no braiding. So the meromorphic tensor case is just chiral, and meromorphic braiding is chiral E1. And what I mean by chiral E1 is that there's some sort of chiral OPE product, and then there's a topological tensor product, and the two are compatible. And there are fancier ways nowadays to talk about these things in terms of categories defined over a suitable configuration space with local constancy conditions. I am not going to try to do that or go into it. I have my own working model that I think doesn't agree with any of these, or sorry, is not exactly any of these. I think I should agree with all of them. One
Can you,
to
sorry, Tudor. What
yeah.
do you mean by the operator product expansion and the topological expansion to be compatible with each other? Can you
Yeah.
explain what that
Um,
means?
yes. So um, um, sorry, I'm thinking of
It, 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 it,
reasonable
it,
things to say.
it's okay. You can deal with it in the end. I don't want to interrupt
No. I sorry,
flow.
I wasn't planning to deal with it at all. But certainly have um, in other talks and things I'm doing. So um, one way to say it is the following: there, um, if you try to take a product of two lines, so the lines need to be fixed uh, in their point on the holomorphic plane. Um, they 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 um, they can't sit inside the holomorphic plane. They need to just sit at a point in order to preserve the symmetries of the setup. Um, and if so, first for every point you choose in the holomorphic plane, the lines that now sit in the topological plane have to have the structure of lines in an entire 2D TQFT. But there are multiple points you can choose in the holomorphic plane, and there's an operation of there. One expects there to be an operation of if you of sort of taking an OPE or re-expanding, and I don't mean colliding because you can't move two holomorphic planes to sit on top of each other. That's not allowed. But you can take whatever's happening in one of them and say, are there operators in the other one? Say you have something happening at Z and something happening at 0. you can say, are there operators at zero that are somehow equivalent to whatever's being inserted at z? Um, um, that's the same question one asks when trying to define an OPE of local operators in 2D conformal field theory. Um, there are like Taylor expansions that allow you to take an operator at one point and re-express it at another point. And there's an actual OPE. If you have two operators, you can say which set of operators at one point is equivalent to the pair. However, one cooks up this operation and axiomatizes it, it needs to commute with everything that is happening in the topological plane, where you have a monoidal category with duals. At least some objects should have duals. And there are coherences that tell you how this like re-expansion or OPE in the holomorphic direction is commutes with whatever you're doing in the topological direction. That's roughly the idea.
Okay. And is it a tedious process to check? Like how are there criteria that could shortcut this to
Yeah.
for you to
So
know if there is this compatibility or you are violating?
yeah. So I'll I'll give you all I've ever needed to work with, but I can't give you the sort of answer that it would be nice is to start with a like a category over the round space and then pin it down at a few points. And it's like the round space of C times R, and pin it down at a few points and say like what minimal set of coherences you need. Um, I suspect that exists. I'm not an expert in it. Um, the
Yeah, I'm a bit confused because for the run space itself, you first of all, it's complex one-dimensional thing. I do not see the place for the real line. If you
but
work
there's but
with this McPherson configuration spaces, but yeah, you have all real dimensions, but then you should add the two-dimensional foliation structure with transversal complex structure. Probably this is what Denise did in what you call chiral E1 category or whatever. Yeah, because
um,
it,
the minimal thing you need are I think you need and is what actually you get in representation theory are two tensor products. A standard monoidal product and an OPE product, um,
so,
and coherences between them. Um,
okay, great. But hold on. But this standard monoidal, probably that's what you refer to the topological plane, yeah? And
yes.
and the other one, OPE, whatever, it's holomorphic, like yeah, that's true. Certainly, it it's a bit strange. You say that there is an E3 structure somewhere because two products compatible with each other. It looks more
There's
like E2
It looks like
structure.
more like an E2. You know, it totally is an E2 structure, right?
Ah,
That's but it's not exactly. If it was E1 E1, it would be an E2 structure, except
and now,
it's chiral on one side.
yeah. Okay, now it's sort of a 2+1 or whatever. Yeah, chiral replace something of the spirit of E2 probably, or something like that, because you have this OPE, you can collide points. It's like configuration of it morally can
It
collide.
is except yeah, it's I guess yeah.
Yeah, yeah, it's good. Yeah, you see that it's difficult for imagination. Yeah. All right, so go ahead. Yeah, placing vacuum at infinity.
So
A bit
there's
more.
one way that these categories had been represented, which is how Costello came up with this construction of the Yangian and 4D Chern-Simons, which was using doing things perturbatively where Koszul dualities can be harnessed, and there's a construction that lands you on representing by the Koszul dual of local operators. And that's the thing that Kevin computed using Feynman diagrams and so on in actual field theory.
But kind of philosophically, you can reconstruct finite dimensional UQ of G starting from the usual Chern-Simons, which is 3D. Topological, purely topological. Then you add this holomorphic direction, which again, philosophically should mean that you can add the loop variable to your Lie algebra. So then probably in the end you should have something like either Yangian or UQ of G hat.
Yes. And the two are closely related, but it's sort of important to keep them distinguished. So if you take your 4D holomorphic theory and compactify on C star, so in other words, take the holomorphic direction not to be C, but to be C star.
Yeah.
Then it looks exactly like a 3D fully topological theory with loops. With loops in the field space.
Still holomorphic Chern-Simons on C star product R2, yeah.
Yes, but holomorphic Chern-Simons on C star product R2 can be rewritten as ordinary Chern-Simons for the loop group.
Okay. Yeah.
You take the radial direction in C star and just treat the thing as an ordinary three-dimensional topological theory. And that's where the quantum loop group shows up. That is not what represents line operators in the 4D theory. If you want line operators, you need to compactify not on C star but on a cigar. So you close off a tip of C, and you put the lines at that tip, and so you sort of get a half space of this 3D loopy Chern-Simons with lines not on the bulk but on the boundary. That's the thing that the Yangian should represent. I think making that philosophical picture precise is still for various people work in progress.
I believe that. Only again, philosophically, C star should correspond to trigonometric version, which means UQ of G hat, and C itself should be rational, which is a Yangian. But probably from the physical point of view, it's highly non-trivial to add this zero.
So just so like the Yangian is sort of half of the quantum group algebra. And the reason for that half is because it's lines in 4D as opposed to lines in this 3D compactification. There are theorems relating the representation theory of the two, and that's just because you can take a line in 4D and reduce it on C star.
Okay, go ahead.
In this Koszul dual picture, local operators in 4D HT theories form a Poisson vertex algebra with a lambda bracket that has, I was going to say it's been computed. Its character is the thing that people call the Schur index in the world of 4D n equals 2 theories. And the actual algebras are the things that Beeman, Rastelli, and company discuss in their work. causal dual of these things are expected to be Yangians or Yangian-like structures. And I'm just mentioning this as expectation. I don't know of any case where this has actually been made precise beyond leading order. But the lambda bracket and local operators is meant to dualize to the R matrix. That's not how, say, Kevin computed the R matrix for the Yangian. Okay. I don't want to use causal duality, and I simply want to ask, what happens if we try to do something with boundary conditions instead? And the boundary condition analysis is not necessarily perturbative in the sense that everything has to be generated by the identity. And it gives a little more structure, which matches various things that have appeared in math. So I want to assume that there do exist boundary conditions that can be placed at points in the x direction. So the boundaries have one holomorphic direction and one real topological direction, and are topologically invariant along RT. And I'll impose the same transversality conditions that I mentioned before. Then a fiber functor can be constructed on lines by sandwiching lines in the x direction between the two boundaries. Because of topological invariance in that x direction, that the boundaries can be approached very close to each other as long as you're sitting away from the line, and they annihilate. And what you get is a little raviolo. I mean that in a precise sense. It's two formal disks glued over a punctured disk with filling, with the line and the bulk theory sitting in the middle, and the fiber functor is evaluating the space of states on that raviolo. What one ends up with in this sort of construction is an algebra that's the tensor product of algebras constructed from each boundary separately, which do represent lines on the opposite boundary just as before. I won't talk about that. Each of these separate HDs and HNs have various structures that come from geometry or configuration space in the same way that they did in 3D. They, first of all, are each vertex bialgebras. And by that I mean that there's a product, and that comes from a collision along time, and there's a vertex coproduct. And the vertex coproduct is the thing that's going to represent the OPE of lines. Lines separated in the holomorphic direction, when squished in this sandwich, due to transversality, automatically break up into, or if you have a raviolo with two lines inside, it'll break up into two separate ravioli with each containing a single line. That's one coproduct that appears, and I'm specifically calling it the OPE coproduct. It does not need to be regular as z goes to 0, and so formally it's valued in Laurent series and Z inverse. On the other hand, if you're really able to come up with honest boundary conditions like this, this coproduct ought to be completely symmetric. so doing it in one order or another may mean wiggling L and L prime in the topological direction a little bit. That has no effect on this monoidal structure. And there are different ways to try to argue that. But and also if they're just right on top of each other they're separated holomorphically, but not separated topologically, that's an operation that makes sense. So one expects something symmetric. On the other hand, one can use a different equivalence between the fiber functor applied to a pair of lines and the tensor fiber functors applied to each of them separately, coming from completeness, coming from the fact that we can insert an ND pair in the middle in glue. And gluing in this case, for degree reasons, turns out to be trivial on these vector spaces. It's not always trivial. Sometimes it gives more Cartan deformations. Here it cannot. And one gets a different sort of a different monoidal structure. And so a second coproduct on this algebra Y that involves both the N and D halves. It's not a coproduct on either half separately. It needs both of them. We can so it's defined for lines that are separated one way or another, definitely in the topological direction, so that we can insert N and D between them. But they can also be separated holomorphically. That's totally fine, and that's holomorphic separation is just accomplished by a translation. And so one gets a second Z-dependent coproduct that's regular in Z, and when Z is equal to 0, it's just a standard coproduct.
Tudor, can somehow naively one can think about the moduli spaces of holomorphic stripes with points inside, and then as usual the structures appear when you degenerate it, and there are two types of degenerations which you allow, which gives you the upper one, like two raviolas type of things, and 2 points and 2 separate holomorphic strips.
This would be nice. I do want to, yes, I do want to point out that everything is three-dimensional here. The vertical direction is complex. I don't know if that affects.
Topological is transversal to the slide, or the other way around somehow. You have to.
So the way I'm drawing things, there's a topological direction that's horizontal. There's a holomorphic direction that's vertical that I'm collapsing down to a single direction so I can draw it. And there's a second topological direction that is transverse to the slide, along which all of the lines and boundaries are extended.
Okay, so it's like in transversal to the slide direction, there is a movie of these pictures, depending on the time.
Yes, absolutely. That's the category direction. Transverse to the slide. That's where morphisms in the category live, or where natural transformations live.
It's more complicated than just a moduli space of holomorphic stripes. Yeah, but still, morally, it's a moduli space. Yeah,
I agree. Yes.
Okay.
The expectation from this second product, the second coproduct, is not that it's symmetric, but there does have to be an equivalence of some kind, certainly because, sorry, before I apply the fiber functor, before I start splitting things up, line operators L and L prime separated holomorphically and topologically should be equivalent if I swap the topological separation, just because that is a topological direction. That should be an exact, or like a exact and cohomology operation. How that gets manifested after applying the fiber functor and splitting things up might be complicated. What one requires is an equivalence. Or in terms of the category, one wants a natural transformation around natural isomorphism, and in terms of the algebra, that's where the meromorphic R matrix comes from. So what you would want in the algebra that represents the stuff is an invertible element, possibly singular in Z, that sends the coproduct to its opposite. Finally, I can do separation both holomorphic and topological in the top picture and the bottom picture. And again, if I haven't applied any fiber functors, these things are equivalent. And that requires, after I start applying the fiber functors and splitting things up, to get a coherence between the two. And that leads to a Drinfeld twist, that, or as sort of a meromorphic version of a Drinfeld twist, that should conjugate the first coproduct to the second. That in particular implies that the R matrix that appeared for the topological coproduct is factored into the Drinfeld twist and its conjugate. So that's just summarizing everything on this slide. That's sort of the package one gets, or the optimistic package one gets from boundary conditions. And I sort of think of this as the analog in 3 dimensions as the quantum group being a perfect Drinfeld double. Here, what that seems to mean is that there are 2 coproducts. One of them is incredibly nice because it's symmetric, but it's singular. The other one is very nice because it's regular, but it's not symmetric. And the 2 are related by a twist. I want to point out that this sort of structure has appeared in studies of the Yangian, but to point that out, I need to mention a small generalization of the whole setup. And I see that I'm totally out of time. So
maybe you'll say something about BPS and CoHAs, because it's in the title of your lecture.
Yeah, I can do that, and I can say maybe a little more tomorrow.
Yeah. Okay. It's up to you.
No, yeah, I'm happy to do that. So the sort of setup with 2 coproducts related by a twist, where they have different nice properties, appears for the standard Yangian. And it was described very nicely in work of Gautam, Toledano, Laredo, and Wendland. For the standard Yangian that corresponds to Chern-Simons, there aren't actually boundary conditions. There are interfaces to a free theory, which is Chern-Simons for the Cartan. In this sort of setup, the algebra we get is not just a tensor of the algebras on the 2 sides, but it involves whatever represents the category of modules for the Cartan, which is the Yangian for the Cartan. One would hope for some chiral double bosonization construction, spelling out all the properties of that thing. I don't think it's ever been written down. It'd be really nice if it was. The upshot from this like two different coproduct analysis when the outside is not trivial is that the OPE type tensor product is, or the OPE coproduct is controlled by the R matrix on the outside. And so that's not necessarily trivial. And then the R matrix for the topological product is obtained by twisting the R matrix from the outside. And that's the structure that actually appears in the Yangian. What I've been calling the OPE product is known as a deformed Drinfeld coproduct in this setting, sort of generalizing what Drinfeld did for quantum loop algebras. And the free thing is the abelian R matrix. So this structure does appear there. Okay. I think I actually will say things about BPS states next time, because there's quite a bit to say about how that all fits in. So if it's okay, I'll stop there.
Yeah, it's up to you. You are the speaker. You know. Yeah, very, very interesting. Are there any questions? Too many. We should absorb it somehow, because you see, you start with some physics which we do not understand, then you end up with some mathematics which we do understand, but this link is not mathematically is kind of missing. This double cartan, yeah, it's a construction. I believe I read it in this one of Finkelberg's papers long ago. Yeah, it's on the quantum group side. Yeah, I recognize it, but from the other structures, yeah, it's. Yeah, it would be nice if indeed these, you know, like any algebraic structure comes more or less from algebra or prop over opera, that's topological nature. So you have some moduli space, you take whatever chains on this moduli space, and so, or whatever you want, forms, if you can, and then you produce your structure. So it would be nice if this will be of the same type of thing. So okay.
Yes, I think I'm not the person to do that. I I can understand what people from this school are saying, but yes, but I agree. This would be fantastic to describe.
Yeah, because currently it looks like sort of for me,
Yeah.
like
So I think
with
if you were
discrete
like
topology.
if you were having this conversation with Sam Raskin or Gatesker, you would get very different answers.
Yeah, but that
And
comes
you
another
get something in that
problem
flavor.
to understand what they're saying. Yes. Yeah,
Yes.
okay, yeah, all right. But
And
maybe
also,
I
yes.
will.
So I just read the chat. Totally. So I mean, the mathematical definition of the raviolo is two disks glued over the punctured disk. In the formal sense, where each of them is like spec of Laurent and Taylor series. It's that non-Hausdorff scheme. I'm not sure that I would need to think a little bit about what adding filling means.
I don't know. I mean, you can again naively think that you have something like, you know, like something three-dimensional with transversal complex structure. So if you imagine the sphere and the foliation by lines which intersect that sphere, then the upper half and the lower half, if you mod out by the foliation, they should be kind of two formal disks with the center identified. Yeah. So, but it's a naive picture, which kind of mathematically now indeed well understood. Yeah, by people doing this, whatever, like BFN construction, and there is even Raviolo vertex algebra, which is part of what you said, but yeah. Okay.
Yes. So another way to say what this category is that it's a categorification of the Raviolo vertex algebra.
Yeah. Okay.
For what that's worth.
More questions or comments? All right. If no question, well, thank you very much. Again, as interesting as it was last time. And tomorrow,
thank you all.
Tomorrow Tudor will give his last lecture. The time will be different. It's 11 a.m. in Kansas, and you can add whatever number of hours in order to get your local
So
time.
I thought 11:30, yeah? Or is it 11?
11:30? I think you said
Nope,
11.
11 is fine.
11.
Great.
Okay, 11. Okay, good. This is it for today. Thank you, Tudor.